I will now today start off with a little bit offbeat processing, which has been really used very effectively first by the Japanese and later on by the Chinese also. This is called the vapor infiltration process. You see, one area, let's talk of ceramic armors. Where are these used? These are used in tanks, in troop carriers, and also as body armors of the top level. You have seen in the Bombay blast case, the person was killed because he was not wearing the proper quality of armor which was required to stop the bullet. Today, ceramic armors are available which can stop an AK-47 bullet which is traveling at over 1,000 kilometers an hour fired from 20 feet away. It can stop an Uzi submachine gun. Now, these are of very complicated designs. If I find time, I'll bring them up. But why I brought this up is here, so far I've been dealing with powders. Here, two different materials are coupled together in a fashion so that they are really called composites. One fiber matrix in another. This process, this is done by vapor infiltration. A very simple standard technique would be this. We have a chamber over here. In here, let us say we have got silicon carbide fibers woven in form of mats. It means essentially devoid of the technical language. It is that, assume this layer of shirt I am wearing, this cloth, assume it is made up of silicon carbide fibers. These are woven 90 degree. And over here, this layer of cloth which I am wearing is placed stacked up. And this is what is called the fibrous preform. And further, not only the preform there is aluminium metal. Now, this is a graphite holder. Aluminum oxide won't react with it. There is a lid through which gases can go out. What is done is this whole thing is heated by an induction coil. The aluminum melts. So, what would happen? It is something like this, that I've got this layers of cloth or my handkerchief. Aluminium melts and percolates right through every single layer. After that, and when aluminium is percolated through all the layers, reactant gas here I could put in oxygen, so that aluminium reacts with oxygen to give me aluminium oxide. So here I would have silicon carbide cloth layers with aluminium oxide interwoven. If I look at the cloth, I would see under a microscope, I would see just this picture. So first the aluminium has melted, then it has been oxidized. I would see the silicon carbide, the aluminium oxide, and also unreacted aluminium. What is done is, this is then cooled as if it is, this is a silicon carbide cloth, it has got layers of alumina inside it and aluminium oxide also inside it. When it has been cooled, the surfaces have become impervious, so they are machined. To expose the pores, and the vapor infiltration is done all over again, so that I have got now a dense silicon carbide reinforced alumina matrix. This is in a very simple stage what is chemical vapor infiltration. What I could do is, I could also reverse it. For example, I could have had in the chamber, in the hot zone, sorry, the inlet, gas inlet, I could have had alumina fibers, stacks of woven alumina fiber cloth. In that case, what I would have done is, as this is heated by an induction coil, this is a graphite block, so heating is not a problem. I would have passed trimethyl trichlorosilane, this gas. This gas decomposes to give me silicon carbide plus 3HCl. The HCl is pumped out. So here I would get within the alumina silicon carbide. So I would, of course, this is still not impervious. It has to be taken out, machined to clean the pores, again infiltrated to get a very dense matrix. So by changing, I can get Al2O3 fiber in SiC matrix. I can get SiC fiber in Al2O3 matrix. I can get any one of them. I can switch depending on what I use, both of them. Now, before we do this, this process is basically helps us to make a composite where the fiber reinforces the matrix. This is the only way I can put a ceramic fiber in a ceramic matrix. If I had taken, for argument's sake, silicon carbide fibers and these are SiC fibers, fiber mats rather, and had put in Al2O3 and tried to melt the alumina so that it would form the matrix, I would never have been able to get the silicon carbide reinforced aluminum matrix due to a variety of reasons. One, thermal expansion mismatch. At those melting, alumina will melt at 2075 degrees centigrade. There will be an interreaction between the silicon carbide and alumina, which would be disastrous. Why? Because if this is a silicon fiber and the matrix is chemically bonded, what would happen is it would not be acting as a composite. What would happen is the alumina matrix would break and the silicon matrix, carbide matrix would break. In chemical vapor infiltration, one of the first thing is done is the fiber mats are coated with a debonding material. The fiber mats are coated with a debonding material. The simple reason is, if this is the alumina oxide matrix and there has been a reaction between the aluminum oxide matrix and the silicon carbide, when the fracture goes through the alumina, it will also go through the silicon carbide. However, if there is a debonding material, what would happen? The fiber would slide out and the basic structure would be retained. So, the first thing in chemical vapor technique is infiltration technique is that the fiber mats have to be coated with a debonding material so that the fiber can slide and avoid debonding or simultaneous fracture. Here in this process, the gas can be chosen so that it either dissociates like I did with CH3 SiCl3, it dissociated, or B reacts as I did with Al plus O2 to give me Al2O3. So, here by successively vapor infiltrating, reacting, forcing the second phase to form, if there is a liquid, the liquid is oxidized, cooling, then abrading to open up the surface, and again vapor infiltrating. By doing this multiple times, we can get a very dense ceramic fiber in ceramic reinforced ceramic matrix, which causes reinforcement. What are the advantages of this process? The advantages is very simple. We are working at less or equal to 1000 degrees centigrade. So, fiber damage is very low or nil, because if we had been working at a higher enough temperature, the material the fiber could have dissociated the surfaces and there were other problems. Second, the fiber mats can be made with very high purity. For example, when I talked of alumina fibers in silicon carbide, what I had in mind was alumina fibers made from alkoxide based sol gel process, in which case the alumina fiber mat is 99.99% pure. Because the advantage, I do not have any glass making phases. The material does not melt at high temperatures, at low temperatures. Third is, because the temperature is low, mechanical stresses are low. Due to the very nature of the matrix, it is very resistant to thermal shock. Five, creep and oxidation resistant. And most of all, ideally, we can have any combination of fiber and matrix. What I would say is, like say silicon carbide in fiber, zirconium carbide matrix, even as esoteric materials as this. However, there are certain disadvantages. Because I go back to the diagram, the vapor has to infiltrate, undergo a chemical reaction, nucleate between the fiber mats, and then due to the fineness of the size, self-sintered. The process has to be very slow. It may take weeks to make a single fiber reinforced matrix. Second, if you remember, I said that when I was working on this, these were oh, not this one, yes, this one. These were silicon carbide fibers. There was aluminum metal that was allowed to percolate. There were aluminum oxide I had said particles which had been formed, but I did also say that there was some molten aluminium also, which means this material will have relatively high residual porosity. (15 to 20%). And of course, being a chemical vapor deposition process which takes a lot of time, it will have high production cost. Though this production cost is offset by the user needs. This is one of the only methods that allows you to tailor the fiber and the matrix and integrate them into each other. So, if you are looking at defense purposes or personal protection purposes, the high production cost can possibly be justified in most cases. However, this method of production has gone into the market. Ceramic armors or these plates are available, but yet one of the biggest problems is the nucleation, growth, sintering, the essential things which has to happen when these particles which are over here, they join together to if we have to get a very dense matrix. If we have to remove this residual porosity, we really have to model and understand nucleation, growth and sintering of the vapor deposited matrix material in the fiber. And as I said, this is already commercial production even with such a high residual porosity. The Japanese, the whole process started long back where the Japanese invented the Langside process. I had referred to it in the last class. And ever since then, chemical vapor infiltration has been a major technique which is being developed for various purposes. Now, because most of the information is in the proprietary domain, I'm unable to produce any more information for fear of violating the intellectual property rights of the other companies. I brought this in because this is a very fast developing field. Now, the second item of my class was casting. There are two I will take. One is tape casting. The other one is slip casting. I had referred to them in my earlier lecture when I was talking on binders, deflocculants, surfactants. In fact, I had initiated discussions on tape casting, and you had seen a video on slip casting. First, let me go on to tape casting. Why? You see, by this method, by tape casting, if I can get this is this paper, but if I can get ceramic tape like this, what I can do is I can make it, fold it, and these are used as rocket nozzle inserts. When the rockets fire, this is the metal. What protects the metal from the searing heat of the gas flames, whose temperature can rise to 3000 degrees centigrade? Here there are ceramic inserts which protect the rocket nose cone, and that comes from ceramic tapes of such thicknesses which are tape cast and then used as rocket nozzle inserts. I had schematically shown last day what is tape casting. Now let us see what it is. Here you see that a knife is moving continually and a slurry coat is forming over here. The uniformity, you should notice that the slurry viscosity is such that it is not spilling over. It is just being coated very uniformly and in a very continuous fashion. That was how tapes are cast. I had said last day that we have a flat surface, I have a doctor blade, there is a gap between this and the doctor blade. I pour the slurry over here and move it. As I move it, the slurry comes out through the doctor blade and forms a coating on it. Now here, so far so good. I had already talked of the various compositions of, say, barium titanate materials which I could use for tape casting. I did that yesterday. Again, I would not like to repeat all of that again because it is in that lecture. I had even given you the process diagram. How would I prepare this slurry? So, I will not go over it and rather let you look back at my earlier lecture where I talked of the deflocculants and everything. Let me talk of what happens after the tape is cast, because this is the platform on which the tape has been cast. Now, this is just like a slurry of uniform thickness, uniform dimensions on a glass plate. What do I do with it? Until I can physically dry the slurry up and physically lift it like this paper from the top of the glass plate. So, now the first question is A, how to dry it? Means remove solvent. That is the first question. Then the question comes, how to sinter it to get a dense tape for end use. These are the two major things I have to deal width once I have cast the tape. Now, let us look at this surface. This material has got a solid loading of about 80% by weight, but if I convert it to volume, it will be hardly 20% by volume. It will have about 80% by volume of the solvent. Now, if I leave this tape, on the table to dry, what would be the problems I would face? The first problem I would face is that the solvent would evaporate very fast from the surface, because this surface is exposed to atmosphere. Solvent would also evaporate from the sides, but the bottom, that would remain solvent rich. So, what would immediately happen if I let this unequal evaporation to go through? The tape would warp, wrinkle, because when the liquid goes away from the top surface will contract due to surface tension. The liquid is going away while there is plenty of liquid at the bottom, so it would warp or wrinkle. So that this tape would by then appear as I run the best case scenario. If this is the side view, if I am looking at the top view, what I would see is the tape has wrinkled also at all sides, and that the edges are frayed because the solvents have gone away from the sides at different rates, and it would have warped in both this direction and in this direction. Well, this shirt I am wearing, after I have washed it and dried it, it will be full of wrinkles. I have got a wonder equipment called steam iron, with which if I press the shirt, the wrinkles go away. But how do I make these wrinkles and everything go away in a green ceramic body? It's not possible. The ceramic would fracture. So, what is done is controlled drying, which is almost akin to what I talked of when I was talking of fabrication of zero-gels from alkoxides. I told you that I would control the temperature, the relative humidity, so that the pores collapsed uniformly and the material did not fracture. So, here my only avenue is to have controlled drying. And how is it done? If this is the platen, if this is the tape that has been, if this is a green tape, green or unfired tape, what I would do is I would cover it up with a glass or whatever sized vessel, so that the vapors which went off did not get lost in atmosphere. As the vapors went off from the surface, the gas phase here got richer in the solvent, and as evaporation proceeded, the gas phase would get richer and richer, and the rate of evaporation would drop. However, it would be, I think, better if we had a container containing the solvent placed within the chamber, so that evaporation of the solvent caused the inside of this chamber to maintain a humidity or vapor pressure which is near about the saturated vapor pressure of the liquid in air at that temperature. So, if I have to dry this green tape, the first thing I have to do it is cover it up and then have some solvent inside that vessel, so that the rate of evaporation of the solvent from the green tape is very, very slow. And this very, very slow means I am talking of days, weeks. But then it may be jolly well that it is worth it simply because of the purity of the products. So, here we used controlled atmosphere to do the drying of the ceramic tapes, and once it has dried, it is then sintered. Here, of course, most of the major technical problems crop up while sintering. Okay, I have used uniformly graded powders with controlled particle size. I have prepared the slurry myself and have cast it, so there is no chance of any contamination coming from anywhere. So, yet during sintering, again warping, wrinkling, both of them occur. So, what is done to avoid all of this? These are all empirical methods. Most of the practical methods are in the hands of the industry. What I would do there is, if this is a platform, this is a green tape, this is the container containing the solvent to maintain proper saturated vapor pressure, and then cover it. In spite of knowing everything, what I do is cover the tape, the green tape, up with another fired tape. The whole idea is, if I have a fired dense similar tape on top after casting, what would happen? The pressure of this material would help the tape keep flat and not wrinkle. Now, this tape casting process is used, as I said, for making large sheets of a ceramic, say memory devices, ferrites or magnetic devices. These tape cast materials are packed one over the other, so that they occupy only a small space on the floor, and the growth is much more larger. So, in order to keep the tape flat, we just put a sintered dense tape of the same material to prevent it from warping. But do we really manage to avoid warping? I guess not. But yet we try to minimize it. Now, these tapes are also used as capacitors, in which case you have these are the two, and this is the dielectric layer. These are in the form of powders. This can act as a capacitor. But when we are talking of devices, we want very, very high values of capacitance. So, what is done is, after tape has been dried, suppose let me say I want to make out of this flat, this is a green tape, and I want to make capacitors with parallel plates using this material. A very convenient way would be stack as many layers one wants, and then punch it mechanically so that the sections are cut. That means I would put all the tape layers stack one of the other, then say bring in a punch. So let me say this is my punch. I press it, the center circular piece comes out, which will have an appearance like this. Now, here it is not only the appearance, the contacts are also very vital. So, on this side the contacts will be this, this and this, so that which is connected to an outer metallized layer, so the current or charge can flow. Right. So, this is the way basically doctor blade tape casting is used by the industry. The next one is from tape casting. I am going to slip casting. I had shown you an excellent video of how the crucibles were made yesterday using slip casting. Now, when you are seeing that video on slip casting, what I said was the slip has to be very consistent. That is, the powder distribution into the slip has to be very well. This powder distribution means the powders in the slip should not fall down. That is, they should not spill over. And give a profile like this. That is, most of the particles have settled over here. There are very few particles over here because the particles have separated. How to do this? I did talk of deflocculants to keep powder in suspension. In suspension. What are these materials then which help deflocculate? I had given you an entire list last day, but today let me give you a little more to show how wide the list of deflocculants can be. If I look at the organic side, and I did not mention any one of these yesterday, is humic acid. Then I talked of lignosulfates already. I talked of polyacrylate compounds. What would I say? Oh, gum arabic. These are organic deflocculants which I had not talked of, but these are very natural. They are available in nature. And in inorganic, I have Na2CO3, I have Na2CO3, K2CO3, sodium hydroxide, sodium silicates, and I said I did talk of this phosphates which has been banned and pyrophosphates. The basic function of these deflocculants is to neutralize the charge on the particle so that they do not coagulate. This is the deflocculant. This is the viscosity. Yes, this would be ideal. Here I have the least viscosity, and this is the ideal place for using the amount of deciding on the amount of deflocculants. Among the other deflocculants which I have not talked of, one is a very interesting one, barium carbonate. Barium carbonate by itself does not cause deflocculation, but it allows, there is plenty of sulfate particles in solution. It combines with that, gives you barium sulfate and a carbonate. This barium carbonate acts as a pseudo deflocculant because the carbonate group on barium carbonate is partially soluble, and that is the best way to cause the particles to stay in suspension. There are other deflocculants also which are used, even tripolyphosphates are used, and barium carbonate I have already said, a lot of these are used. In each case, if you remember, I have to prepare a slurry. This is a good video, and this says what are the tips for casting the slurry of the mold. What the gentleman does here is he pours the slurry into the mold. You can still see the slurry is quite thick, and the slurry is pouring over. During this time, as the slurry is pouring over, what is happening is, you will see a bit later, that you can see that a lot of water has been absorbed. He blows in, there is this coating which is forming over here. Let us see what he does. What he has done is, he has inverted the whole plaster of Paris mold to drain the water out. Here he is cutting the top surface of the mold, the extra part, let the water dry still more, and then he inverts the whole plaster of Paris mold onto the plate. He taps it, and this is the vessel that comes through. This is fundamentally the tape casting process. There are various formulations possible. You can have a one-piece mold, you can have a two-piece mold, and you can do whatever you want with it. What I would ask you is, go through this YouTube. It has got various demos on how slip casting is done. Plaster of Paris is free, is very cheap. Buy it and try any one of the demos. That would be the best way to learn how to do casting, especially slip casting.